All right, so as you can see, kind of our goal today is to find the zeros of a polynomial function, and then we're going to use this to create a graph from the factored form. So basically, we're going to see today how can we make like if we have a polynomial function like x to the fourth minus 2x cubed plus 3x squared, like how could you get a sketch of this without a calculator? Um, Basically is what I'm going to show you how to do today. Just keep in mind zeros is another word for x-intercepts, or sometimes we call these the roots of our equation. Um, but basically what we're going to do is solve, like if you remember when we were solving quadratics, like we were factoring figuring out what our x values would equal. That's basically what we're doing with higher ordered powers today. So some basics. And crap, here, let me pull my key up here really quick just to make sure I don't put anything wrong or forget to say something. But like I was saying, just to even kind of start, like a zero is another term for x-intercepts. We also call these our solutions. And we also call these our roots. I think if there's anything else we call them. Like there's a lot of synonyms we use to kind of mean basically the same thing. Roots, solutions, x-intercept, zeros. I think that's it. That's all I can think of, at least off the top of my head. But and basically these all these things basically just tell you where your function intersects the x-axis. And these can be useful because a lot of times when you're like, for example, if you're modeling like a rocket launch or something, like if you can figure out where your x-intercepts are, that'll basically tell you the time. A lot of like, so like if you had something crazy like a rocket that, I don't know, maybe it like curved and did all weird crap and then it finally hits the ground. Like if you could find your x-intercept, you could basically figure out how long it would travel for. If you had like a, I don't know, a rocket or something doing some crazy kind of curves, you could figure out how they would, like, or for maybe a better example than a crazy rocket would be, I don't know, if you had like a ball bouncing or something like that. But that's why usually it's important, like a lot of like an easy application of using these roots. To find our zeros though, the first thing we're going to do is make sure that our polynomial is in standard form. Like you want to make sure, basically standard forms, like you have like your highest power first, then your next highest power, and then all the way to your constants. So like, for example, x to the fifth plus x to the fourth plus 2 would be in standard form. But if you had something like this would not be in standard form because you don't have the highest power first. So that's what standard form means. I'm going to erase all this because it's a little bit much, but if that makes sense, what we mean by standard form. Um, One kind of like idea, we're going to talk a lot more later on in this chapter, but one thing to kind of keep in mind is that a polynomial function of degree n can have at most n real solutions. So if you have an x squared, like your highest degree is 2, well, you're going to have two answers at like two places it's going to cross at the most. If you have x up to the fourth, you're going to have at most 4 real x-intercepts. Um, but eventually we'll talk about something called the fundamental theorem of algebra that kind of expands on this a little bit later. But so the first thing we're going to kind of show is a lot of times you can write different polynomials in factored form. So it might look a little bit scary for this first example. We have like x up to the third. Like it's not like a quadratic, but anytime you have a higher power function, your goal, if possible, is to see, can you factor this down or can you change that all so it turns into a quadratic? Because last chapter we looked at so many different ways to solve or factor quadratic. So if we can write these problems in terms of a quadratic, a lot of times you can factor them. Like, don't get me wrong, you can come across some things like it's just it's going to be I'm trying to think of appropriate words. It's going to be a big pain to factor it out with conventional methods, but a lot of times you can simplify it into something you know how to work with. So any problem you see if you're trying to factor something down like this, and eventually we're going to learn like a process to do some problems like that aren't like easy to do. There's going to be kind of like a backup plan. But your first thing you should always check is, can you pull out a GCF? So this first problem, you could rewrite this as like, you could pull out an X from all those terms. So basically all your degrees or your powers would go down by 1. And then you want to see like what's inside here. Can we factor this down? It's a trinomial and it's a quadratic. So we could just check, is there anything that multiplies the -15 and adds up the -2? Well, that would be -5 and +3. So you could just write this as x minus 5, x plus 3. And then from there, we could pull out our zeros really easily. Like we would have an x-intercept at 0, an x-intercept at +5, and an x-intercept at -3. If you remember, you set each one of these parts equal to 0 and solve, but they just asked for factored form, so we'd stop. Same idea with example 2. You can also factor out a number part in this one, and you always want to factor out as much as you can, because remember, if you have like a say this was 2x squared, like here, let me use a different color, but say this was 2x squared, well, then we either need to do like group in, or you could do like quadratic formula or something like that to solve it. But usually if you can get the a value to be 1, your life's going to be pretty good. Most of the time you can just factor it out like with like your factor tree, like what multiplies to something adds up to something else. For example 2, you can pull out a 3x. So that would be x squared minus 6x plus 8, right? Make sure my math's not wrong. Yep, okay. But then you can see, can we factor this? Well, yes, we could. What would multiply to 8, add up to -6? Well, that would be x minus 4, x minus 2. So a lot of times, this won't always work, don't get me wrong, but a lot of problems you'll often see, if you can pull out a GCF, you can turn something that you wouldn't be able to factor under other circumstances into a problem you've seen kind of before. Let me check what's going on in the chat. Sorry, there it is. Yeah. And one piece of advice is like you always want, if possible, like if for some reason that was going to be a -x squared, you'd want to probably pull out a negative out of your GCF, because you always want that to be a positive 1x squared if possible, because a lot of times then it will be something you'll be able to factor easily. There are some, like we've seen, there are some problems that can look like this. Like, for example, something that like this wouldn't factor out nicely. Like there's nothing that multiplies to 7 and adds up to 2. So it's not a guarantee, but a lot of problems, if they kind of make them work out a lot of times nicely for you. So always check for a GCF. Eventually later on in chapter 5, we're going to learn about like a rational root theorem, so we can learn to factor things where you can't pull out a GCF, or maybe it doesn't break down into something smaller or easier to work with. So eventually we'll learn methods to deal with those, but you always want to check. Like even if when we learn that new method, it's always worth checking, because this is a lot faster than like the method we'll learn later for problems like these. All right, so that's just kind of how to get it into factored form, kind of use some of the ideas we've seen before. Another thing we're going to talk about is multiplicity. Once your polynomial is in factored form, we're going to find our zeros, but multiplicity is the number of times a solution appears. A lot of times when you deal with higher degree functions or polynomials, you'll have answers that repeat. You might get like 5 twice, or you might get like the answer 2 twice. You probably have seen that even when we did quadratics. Maybe you got the same answer twice. I know there was one on your test where you had the same x-intercept like twice, like you had x equals 1 and x equals 1, I believe. But sorry, it's the number of times a solution appears. So for example, like this one, remember you just solve each, like for example one, you're going to set each one of these binomials equal to 0 and solve, or basically like what makes this equal to 0? Well, x equals -2 would make that equal to 0. What makes this equal to 0? Well, that would just be +1. What makes this equal to 0? Well, that would be +3. So all of these, usually we don't write it, but all of these solutions would have a multiplicity of 1. Usually we don't write the multiplicity unless it's bigger than 1. But looking at example 2, well, you would have x equals 0 from that x on the outside, but then for this inside part, you would have x equals 3, but you're going to have a multiplicity of 2. Because basically, I don't have a lot of space, but basically this is, you could rewrite that as this. So basically, you're going to get the answer 3 twice. So that's what I mean by the multiplicity of 2. So technically, like you could write that 0 has a multiplicity of 1, but usually you don't write it for the multiplicity of 1 because it's kind of annoying to have to keep writing that over and over. So if it's not given to you in, like, so in example 3, let's see how it's not in factored form. We're going to want to try and pull out a GCF and factor this down. But this would, if we could pull it in x, and then I don't know if you recognize that's a difference of squares. So that would really be x plus 6, x minus 6. So I don't have a ton of space. Here, I'm going to just erase that. But that would just be x equals 0, x equals -6, x equals 6, and those are all multiplicity of 1, so I'm not going to write those down like that. It's multiplicity of 1. Okay, you might be wondering, well, so what does multiplicity, like what's the significance of it? So when you have a different, like when you have all of these solutions, if you remember, like these tell you where it crosses the x-axis. So like, for example, in that example 1, my graph would have a point at -2, it would have a point at 1, and it would have a point at 3, like on the x-axis. But what these multiplicities tell you is what happens at those x-intercepts. There's two things that are going to happen. It's either going to cross, or I say that it bounces. So, I guess before we get on to that, we'll kind of take a segue, sorry, with this concept 3. But another thing we often want to do is, if we know our zeros, either from a graph or if they just tell us what they are, we want to see if we can first write it in factored form and then multiply it out to get our standard form. And you might be wondering, well, why the hell would you want to find standard form in the first place? Well, if you remember kind of what we saw last week, if we know our function is in, like what it is in standard form, we can figure out what the end behavior is. So like, for example, well, here, we'll work this one out. We'll talk about what the end behavior is. But if I have something like written, like, well, let's just kind of work through this. I'm kind of jumping too far ahead in my brain. So for example, when the first thing we want to do is write this in standard form. So the first thing you need to do is get your factored form from those zeros. So if you kind of remember when you're solving these, your solutions or your x-intercepts are kind of the opposite of what you had like inside your binomial. Like if you kind of like this x equals 6 came from this x minus 6, it's kind of like reverse. So you're working backwards. So like if you had a 0 at +2, you're going to have a binomial that's x minus 2. If you had a 0 at -3, you're going to do the reverse. So it would be x plus 3. And then x minus 0 is a little bit weird. I mean, the 0 one's a little bit weird. You could just have x minus 0, but one tip, I mean, x minus 0 is just x, right? So so maybe a better way to write this is we could just have an x in front. Like I'm just going to move this to the front, and then I'm just going to copy these other two binomials. So this is our factored form. The problem is we want to get it, so we still got to get it into the standard form. So basically we need to multiply this out. So the first thing we're going to do, I'm just going to distribute this x into the first one. So that would just be x squared minus 2x. And then we need to FOIL this out, and that will be our answer. So the nice thing is they gave us that x minus 0, so at least we didn't have 3 binomials, because if not, we'd have to FOIL basically twice. But if we FOIL this out, you'd have x squared times x is x to the third. X squared times 3 would just be 3x squared. Oops, erase. Then we're going to distribute the minus or the negative 2x. So that would be negative 2x squared. And then minus 6x. And then we just want to combine like terms. So this would be x to the third plus 1x squared minus 6x. Sorry, I'm running out of space. So the nice, like I said, the nice thing about getting a polynomial into standard form is though we can know what our end behavior is. So if you remember, that's a positive coefficient with an odd degree. So that would have like our end behavior, it would, as it goes to the left, it would be going down. And as it goes to the right, it would be going up. Like our end behavior would be down and up. It would look something maybe like that. Like it'd be a cubic function, basically like a positive cubic function kind of looking thing. But that's why you would, if you don't have your polynomial in standard form, that would be a reason to get it into standard form, is if you have to find your end behavior, you can't just plug it into a calculator kind of thing or graph it quick. All right, so any questions kind of moving so far? But basically, if they give you your zeros, you can just kind of put them in these binomials, but you got to flip your signs because you're kind of working backwards. All right, but what I wanted to look at next is basically the end behavior. I don't know if you have your notes from 5.1, but we had that table. Let me just open up so I can write. I don't like, if you remember, we had like a table. It was like even and odd, and then our leading coefficient, if it's positive or negative. Like a positive even goes up and up, down and down. Like if you remember that table, like, but that's how I knew, since it was a positive odd function that goes down and up. Like that would be like that problem from now. All right. But really kind of like one of the big things that I want us to get out of today is basically when you have different multiplicities, remember multiplicity is how many times an answer comes up. What does that do on our graph? Basically, there's two things that are going to happen. If your multiplicity is odd, let me just make sure I'm using the right words. I usually say it crosses. Let me make sure that's what the proper term is. Yeah, okay. So if your multiplicity is odd, it crosses. If your multiplicity is even, I say it bounces. So let's kind of see this visually, what I mean. So let's say we wanted to graph f of x equals x cubed minus 6x squared plus 9x. Well, the first thing you want to do is, like I said, you want to get this into factored form. So you always, especially, all these problems are working out nicely today. Like I said, eventually we'll look at some problems if this method doesn't work, but you always want to pull out a GCF if possible. Because then a lot of times, not always, but a lot of times what you get inside your parentheses is something you might be able to factor. Not always, but a lot of times. So we could factor this trinomial on the inside. What multiplies the 9 and adds up to negative 6x? Well, that would be minus 3 and minus 3. So if we think about this, my solutions, I would have one at x equals 0, and I would have x equals 3, and I would have that answer twice. So that has a multiplicity of 2. So a couple things. Well, first off, I'm just going to plot these x-intercepts. So we have one at 0, and we have one at positive 3. One thing I should have asked, or one thing to think about, what's our end behavior of this graph going to be? Well, it's a positive odd function. You're going to kind of want to learn these, but a positive odd functions, the end behavior is it's going to go down on the left side, and it's going to go up on the right side of this function. That's based on the table. I need to post. I forgot. I just was looking earlier. I got to post the key to the 5.1 note. So I'm sorry. I didn't realize that wasn't open until I looked today. But there's like a table with these kind of end behaviors on them from the notes we took last week. But one thing I'm going to do is I'm going to just draw in this end behavior. So from this point on the left, it's going to go down, and from this point on the right, it's going to go up. So let's look at what I said here. So if you have a multiplicity that's odd, like this x equals 0, we usually don't write it, but I'm going to write it now. It has a multiplicity of 1. So what that means is it's going to cross. So it's like when I draw this in, like it's going to go past the x-intercept. And then eventually it's going to have to come back down to this point here, right? But then look what happens at this point. Since my end behavior goes up, it bounces. Like this is what I mean by bounces. It doesn't cross, like it comes, it touches, and then it shoots back up the direction it came from. But this bounces because this had a multiplicity of 2. This has a multiplicity of 1, so it just crosses. If I could just show you a few examples really quick, like in Desmos here, I'm going to share my computer screen. There it goes. So like say, for example, I had x minus 3, and let's say I had x plus 4 squared. So like this function could look crazy, but the only thing I'm trying to show you is look, like at this, see how at negative 4, that would be a multiplicity of 2. See, so it bounces at this point. And at 3, it's a multiplicity of 1. So it crosses through this point. So how do we know the red line hump thing goes up and not down? Here. Let me go back to the iPad. So good question. So I think that was Brooklyn. But somebody asked, like on my sketch here, if it ever it's gonna load. There it goes. Like how did I know how do I know it would be up here and not down here? Is basically the question. Well, because since it has a multiplicity of 1, I know it has to cross here. And based on the end behavior, since it goes down, I know, like, that's how I knew like this green line was going down. So since it has to cross, you're going to have a hump. And if we wanted to get a more accurate picture, we could find this relative max in our calculator. But for what we're doing right now, like we're just getting a sketch, I don't care what this relative max is, unless I wanted to find like my increase and decrease in intervals. Let's see, let's look at another example though. But basically that's the idea. If you have a multiplicity of 1, it's going to cross through that point to the other side of the x-axis. If you have a multiplicity that's even, so like you have a multiplicity of 2, 4, 6, I mean, you probably won't, like, I mean, it would be unusual to have a multiplicity that high. for what we're doing, but it would bounce at that point or basically go touch that point and then shoot the same direction it came from. But let's look at another problem. So concept 4, now that you've found your zeros, let's see if we can sketch these. So we're going to sketch these without a graphing calculator. You could definitely check these problems really easily in your graphing calculator, but the only thing we really need for like at least what we're doing right now, the only thing we really need our graphing calculator to do is help us find our relative max or minimums. I mean, your graphing calculator can definitely help you with these other things, but like we don't need to use it necessarily. So let's say we had this example. So the first thing is I'm going to have my zeros. Remember, you would just set each one of these equal to 0 and solve. So those would be my zeros. So the first thing you always want to do once you find your zeros is you can put like the points on your x-axis. All of these have a multiplicity of 1, like for all of these. So like they're all going to cross. None of these are going to bounce. The step 2 is you want to figure out your end behavior. One tip, I mean, you don't have to FOIL this all the way out. If you notice all of your x's are positives, like if you multiply this out, you're going to get a degree of 3 and it's going to be a positive coefficient. I mean, I don't care what the rest of the junk is. So you don't need to FOIL it out all the way necessarily. But since it's a positive cubic function, the end behavior would be down and up. So once you know your end behavior, you can draw that in. So from like go to the 0 furthest to the left, it's going to go down from there. And then from the 0 furthest to the right, it's going to go up. And this is a rough sketch. It might look a little, obviously, if you graph this, this isn't going to be super accurate. But since these all have a multiplicity of 1, it's going to cross. So I can kind of draw the rest of my picture. So from, like if I'm starting at my line going up, it's going to cross. And it's going to, I mean, I don't know how high it's going to go. It could look something like this. It could look something like this. So, I mean, we're just getting a really rough sketch, but so it's going to cross and eventually it's got to come back down because it's got to cross through this point. It's going to cross and then it's going to, oops, what's it doing? And then eventually it's going to have to come back up. So this is a rough sketch. Like I said, I don't know, we could sketch this like in Desmos and it might look something like this, or it might go really far down. Like I said, if we wanted to get a better picture, then we would want to use our calculator to get our relative max or mins, because that would basically tell us how far or how high these humps go, if that makes sense. But for what we're doing, we're just trying to get a rough sketch. Like I said, if we wanted a better picture, like I said, we could find those relative maxes and mins from what we've seen before. And let me see, sorry, the chat got stuck behind. Let me see, someone said something. Could it just be a straight line? So how do we, that was your old, wait, so how do we know the red line goes up and not, like, could it just be a straight line through those x-intercepts? Well, it's not going to be a straight, like, it's not like if you're, I don't know if you're suggesting like this, but like why, how do we know it's not just something like that? I mean, the reason we know it's not that is because that would just be like y equals, wait, yeah, that would be like y equals 0. So I mean, I know it's a cubic function, so it's going to at least have like those ends, if I'm understanding your question right. So it couldn't be like a straight line through them. It's got to it's got to have this end behavior, like going up and down. And based on the like the degree, it couldn't be like a horizontal line. Well, since it has to cross through, so it has to at least cross, like it could almost look like a straight line, but it has to go past the x-axis. That's what I mean by if it has a multiplicity of 1, it has to at least cross to the other side. If that makes sense. I know it's a little bit weird. So that's pretty much it for time. Oh wait, here's another problem. This one doesn't have a multiplicity of 2. Here, I'm gonna switch this problem. I just kind of want to make sure we're understanding this a little bit better. Let's say we had something like this. Here, let me give myself more space. because this problem is kind of similar like the one we just did, so that's why I'm changing it. Okay, let's say we had something like this. So well, our zeros, we'd have x equals 2. That's going to be a multiplicity of 2 because like that's the 2 there. We're going to have -2, and we're going to have +3. So, oh crap, this isn't going to fit. Here, let me change my numbers. I didn't really pay attention to the graph I'm given. Sorry about that. So let's do. So sorry. So that would be x equals 1, x equals -2, x equals negative. Wait, God damn it, I meant to make these the other. Okay, sorry, I goofed up my signs. All right, sorry about that. Let's start fresh. All right, so sorry. So that would be x minus 1. Sorry, I was trying to make a problem that would like work with because the graph I'm given, you really only have positive x values to work with. So sorry, this would be x equals -1, x equals +1, x equals +5. This one has a multiplicity of 2. So it's going to bounce at that point. Yeah, we're about out of time. So just if you want to see this, we're actually out of time, but like my end behavior, if this would be an x to the 4th and it's going to be positive, so it's going to go up and up. So at -1, it's going to cross. And like I said, I don't know how far it goes down, but eventually it's going to go down and it's going to have to come back up. But at 1, it has a multiplicity of 2, so it's going to bounce. So it's going to go back down, then eventually it's going to have to shoot back up, like because it bounces here. So that's all I have for today. I will make sure I post these notes, but tomorrow we'll be working on our Delta Math over this. If you want to give it a go tonight, you're welcome to give it a head start, but there's definitely some things I want to say tomorrow about it.